Hi, my name is Alexis Swingenbach, and this is my Physics 2211 Lab 2. Here's our table of contents. So the purpose of this lab is to compare a projectile's path of motion when it's being acted upon by drag and gravity versus when it's just being acted upon by gravity. We learned that drag affects an object's path of motion. So these are the formulas we use. We have R final is equal to R initial plus the average velocity times the change in time. We have Vf is equal to Vi plus F net over m times delta t, and we know that F net over m is equal to acceleration due to Newton's laws. Gravity is 0, negative mg and 0. Again, g is acting as acceleration in this because F equals ma. So our drag force, we have a proportional constant times the magnitude of velocity squared times the direction of magnitude as the negative. So here are some graphs to help us kind of understand what's happening when you throw the ball. So first, gravity will always be pointing down. Your force initial will be up as you throw the ball, but when you let go and it starts to kind of clear that arch, velocity will be pointing downwards and your drag will be pointing in the opposite direction. And as the velocity path goes steeper, drag will also grow steeper. So now we're going to watch that video. Okay, now we're going to look at the code. So the mass of my ball was 0.45. This is estimated. So the position vector we got from using tracker, and the velocity vector I got from doing the change in distance over the change in time for the first few frames of my video. Delta t is size of time step, which is 0.033 seconds. And then our proportionality constant, we did one graph where it was 0.04 and one where it was 0. So then the actual function, we loop it for 0.633 seconds. And first we only include drag if velocity is greater than 0, otherwise the drag is going to be the 0 vector. Gravity is always going to be mass times gravity, so we set that. F net is equal to gravity plus drag, and then we're going to apply our momentum principle, which is Newton's second law, and update velocity and then position. Then we will update the clock, and then this is all visuals for the graph. This is all visuals, and yeah. So now we're going to run it. That happens, and then we get a couple graphs as well as some numbers. So when we put all of those graphs together, we're going to get our experimental curve is going to be this one, the gravity one is going to be this orange one, and the green is going to show us our gravity plus drag. So I know the experimental goes a lot higher, and I think that was because my frame rate was too low and my mass is just off, which I couldn't quite fix. But as you can see, drag kind of pulls the curve inwards and makes the parabola a lot skinnier, which makes it more closely related to the experimental. So now we're gonna get into our what ifs. So, do any of the graphs hit terminal velocity? And my answer is no, because to reach terminal velocity, you have to have an asymptote in your velocity, and as you can tell, there are no asymptotes in either of these graphs. They're both pretty straightforward and down. If I wanted to find terminal velocity, I would drop a ball into free fall and let it fall for quite a while in order to get it to maximum velocity. So another one, if we threw an object straight up, would it take a longer or shorter time? So here I have the two equations that show us time. One is 2 times the velocity initial times sine theta over gravity. That's going to show us if we threw it at an angle, which is what I did. And then we have 2v over g, which is if you threw it straight up. We know that sine theta is always going to be between 0 and 1, and so we know that this numerator is going to be less than this numerator, and therefore this time is going to be less than this time, meaning that throwing it straight up is actually going to have a longer amount of time in the air than throwing it at an angle. So yeah, we learned that drag shortens the amount of change in the x direction. And yeah, thank you for watching.